I'm going to talk about constructive and destructive interference. I'm also going to talk about intensity and decibels. All right? So imagine that you had multiple waves combining. Okay? Maybe somebody dropped multiple rocks into a lake, and so on the surface you had multiple waves created. Maybe somebody has multiple speakers in a room playing music, so you'll have multiple sound waves created and combining. All right? So depending on how waves combine, the net amplitude, okay, from the combination of waves might be bigger than what you had before, or it might be smaller. Okay? When it's bigger, that's called constructive interference. When it's smaller, that's called destructive interference. Let me try to give you a picture to help you understand constructive interference. So imagine you had a wave moving to the right, represented by this blue curve, and imagine you had another wave represented by this purple curve moving to the right with the same velocity. Okay? Can you see that the peaks and valleys are lined up? When that happens, the amplitudes are going to add together and you're going to get a bigger net amplitude. However, what if we had the same blue curve as before, but instead of having the purple curve lined up, what if it was, when we compared it to the blue curve, it was something like this in comparison? All right, and again, you have two waves moving to the right at the same velocity. Can you see that the peaks of one curve line up with the valleys of the other curve? Okay, so they're going in opposite directions all the time. Okay, it's almost like a tug of war. One's trying to move a piece, let's say it's rope. One's trying to move the piece up at the same time that the other one's trying to move that same piece of rope down. Okay, so the net effect, it's going to be like two forces in opposite directions. They're going to end up making a smaller net effect. Okay, so again, the first situation is an example of constructive interference, okay? And the bottom is an example of destructive interference. Now, let me show you some applications in the... A lot of people suffer from kidney stones. Kidney stones are hardened deposits that collect in kidneys for various reasons, and they're very painful, I'm told. All right? Let me show you how you can treat kidney stones without surgery. Give me a minute to make a picture. All right, suppose this was a picture of a portion of someone's body. The red figures denote two kidneys. The blue marking denotes a kidney stone. All right, so instead of going in with a knife to take care of the kidney stone, what if we did this? What if we emitted a sound wave directed towards the kidney stone? Okay, so there's one sound wave. Now, we don't want to harm the person. We don't want to bruise the person, so we don't want to make too high energy of a sound wave, okay? But we'll aim it towards the kidney stone, so that's not going to do anything, all right? However, what if I then emit another sound wave towards the kidney stone from a different direction? Okay, again, that is gentle enough that it's not going to harm the person's body. But can you see what's happening in the kidney stone area? Okay, even though all of those sound waves separately are harmless, can you see that at the kidney stone area, at that one region, the sound waves combine? Okay, if you do this just right, you can spare damaging your body, but you can make a large enough force at the kidney stone area to shatter the kidney stone. Okay, this is a very nice procedure to avoid a very painful surgical experience. All right, so that's one application of constructive interference. And something similar is done with tumors. All right, imagine if somebody had a brain tumor. All right, I think you would agree we don't want to go in and cut somebody's skull open to deal with a tumor. On the other hand, what if we could aim a high energy radiation wave at the tumor? Okay, and again, we don't want to aim so much radiation at the person's skull that it kills brain cells, but we aim enough harmless waves such that they combine at the tumor, and at the tumor, at that one region, that it is harmful. Okay, it's harmful, but only for the cancer cells at the region where they interfere constructively. Okay, so kidney stones treatment and tumor treatment. Those are two examples of constructive interference. Now, what's an example in the real world where you might want to use destructive interference? Okay, imagine that you worked near an airport, or you lived near an airport, and you didn't want to hear the loud plane engines all day long. All right, have you ever heard of anti-noise headphones? Okay, how do you think those work? There's a computer that can analyze the environmental noise, and it's able to create sound that combines with the environmental noise in such a way to cause destructive interference. Okay, isn't that cool? I'm going to talk now about intensity and decibels. Before I do that, I need to specify some wave types. You may be familiar with transverse waves and longitudinal waves. Here are some other wave types or wave classifications. All right, first, planar waves. Planar waves are planes moving all in the same direction. An example of a type of wave that can be a planar wave is a sound wave. All right, sound waves can be planes of compression areas all moving in the same direction. So planar waves. Now, another type of wave, a different type, is circular waves emanating from a point. All right, and the circular waves are moving away from that point in every direction. Think about what happens on the surface of a lake when you drop a pebble into the water. All right, so that's an example of circular waves. Now the next one is like a three-dimensional version of the circular wave type. So imagine that you had spherical waves emanating from a point. Okay? So the circular waves are moving in every direction within a plane, but what if you had waves moving in every direction in 3 dimensions? Okay? An example of a spherical wave would be like the radio waves emanating from a radio station. So the radio station wants everybody in every direction to hear the radio show, right? So they're going to blast their signal in every direction. So those are spherical waves. Okay? Now, intensity is something that applies to waves where you have energy spread out over an area. All right? So you can talk, for example, about the intensity of the spherical waves emanating from a radio station. Intensity is equal to the power of a wave divided by the corresponding area. Okay? Intensity is often denoted by I. So since power is often denoted by P and area by A, a compact way to express this formula is I is equal to P over A. All right. Now this applies to more complex shaped waves than spherical waves, but let me show you how to apply it to spherical waves. So suppose that someone had a radio station that was emitting 100 kilowatts of energy, okay, or 100,000 joules per second of radio wave energy. All right. Now, and suppose we wanted to know what the intensity was 100 meters away from the radio station. All right. So the power is 100,000 watts. 100 meters away, imagine all of that power being spread over the surface of a sphere with a radius of 100 meters. All right. The formula for the surface area of a sphere of radius r is 4 pi r squared. Okay? So the intensity 100 meters away from this radio station is the power divided by 4 times pi times 100 squared. All right? So 100 squared is 10 squared squared, which is 10 to the 4. The numerator is 10 to the 5. 10 to the 5 divided by 10 to the 4 simplifies to 10. So the intensity, therefore, is 100 over 4 pi. 10 over 4 pi. And that reduces to 5 over 2 pi. Or if you like decimals, 0.8, and the units for intensity are watts per meter squared. All right. Now, here is an exercise I will challenge you to do. Can you tell me, using the intensity formula, with respect to spherical waves, can you tell me if you have a radio station with power 10 to the 5 watts being emitted, all right, and let's say we have a certain intensity at a distance of 10 meters. How far do I have to go for the intensity to decrease to 1/4 the value that I have at 10 meters? How far from the radio station do I have to be? All right. Another way of saying it is, if I'm standing 10 meters away, how much farther do I need to be standing away from the radio station so that the intensity is 25% less? All right. Pause the video and see if you can determine that. Okay, so I'll go ahead and work it out now also. So we know that the intensity is equal for a spherical wave, power over 4 pi r squared. All right, and the power being emanated is from the radio station is not going to change. If I cross multiply, I get power is 4 pi times IR squared. So I1 times R1 squared is equal to I2 times R2 squared, where I'm defining I1 as the intensity at some value, some distance from the radio station, R1. So for R1, I'll use 10 meters. And then R2 is what I'm going to solve for. So R2 is equal to the square root of I1 over I2 times R1. R1 is 10, and we said we wanted the intensity to decrease by, to be 1/4 what it was at 10 meters. So in other words, I2 is 1/4 of I1, so this simplifies to the square root of 4 times 10, or 20 meters. Okay, so because of the R squared dependence in the intensity formula, when you double your distance, the intensity gets 4 times smaller. All right, you may or may not have expected that. All right, now let me talk about decibels. Decibels are a way to denote intensity values. All right, they're commonly used, for example, when talking about sound waves. So there are sounds that are very that have very small intensities, like a mosquito flapping its wings, and there are sounds that have very large intensities, like a rocket blasting off. Okay, so when we have such a huge range, one common technique to not have to write zeros all the time is to use logarithms. Okay, and that's what decibels essentially are doing. So the smallest intensity of sound that a human ear can pick up is approximately 10 to the minus 12 watts per meter squared. That's called the threshold of hearing. All right, so what you do to get the corresponding number of decimals for some intensity value is and let me refer to this threshold of hearing as I naught. Okay, so if we wanted, let's say, to find the decibel value corresponding to some intensity I, what we do is we multiply by 10 the logarithm to the base 10 of the ratio of I over I naught. Okay, that will equal the number of decibels. Okay, let me immediately do an example to make that more clear. So suppose that we had a sound intensity of 10 to the 10 Webers per meter squared. All right, so to find the corresponding number of decimals, I'm going to do 10 times the log to the base 10 of 10 to the 10 divided by 10 to the minus 12. Okay, and the ratio simplifies to 10 to the 22. The log to the base 10 of 10 to the 22 is 22. So that whole expression simplifies to 220. Okay, so 220 decibels is equivalent to 10 to the 10 watts per meter squared. All right, now if you understood that, let me let you do a decibel calculation. Okay, so jot the formula down for decibels. I'll put a box around it. Okay, and let me go to a new whiteboard now. So would you please find the corresponding number of decimals that corresponds with respect to 10 to the 5 watts per meter squared? Okay, pause the video if you have to, if you like, and do that now, please. Alright, so I'll go ahead and calculate that as well. So I want to calculate 10 log to the base 10 of 10 to the 5 over 10 to the minus 12, and 10 to the 5 over 10 to the minus 12, that simplifies to 10 to the 17. The log to the base 10 of 10 to the 17 is 17. So this whole thing simplifies to 170 decibels, or some people refer to that as dB. All right?